AI engineering starts with a specific goal: taking a massive pre-trained language model and customizing it for highly specific enterprise tasks. But updating every single weight in a modern neural network triggers an immediate hardware bottleneck. During full parameter fine-tuning, the math demands that the original model weights be duplicated to store optimizer states and gradients. This forces the memory footprint of even a relatively small 7 billion parameter model well past 80 gigabytes of VRAM. That requirement eclipses the limits of standard consumer GPUs and edge hardware, making local deployment physically impossible for most teams. To bypass this hard physical limit, the industry adopted parameter-efficient fine-tuning, or PEFT. Within the open source community, one specific methodology has come to dominate the pipeline. This is known as low-rank adaptation, or simply LoRA. LoRA freezes the massive base model completely. Instead of altering the existing architecture, it isolates and trains a microscopic fraction of new parameters. While this radically democratizes the compute requirements, it introduces a hidden adaptation capacity limit that engineers must account for. Achieving hardware efficiency frequently masks a loss in generalized capability, forcing a critical architectural trade-off. To understand this trade-off, we have to look at the underlying mathematics of how a neural network updates its knowledge. In standard fine-tuning, the new learned weights are added directly to the pre-trained weights. LoRA operates on a different hypothesis, that the specific mathematical changes required to adapt a model to a new task possess a low intrinsic rank. Instead of updating the original weight matrix, LoRA bypasses it entirely. The necessary weight changes are decomposed into two smaller matrices, A and B. A massive 4096 by 4096 square is bypassed by a pair of 4096 by 8 and 8 by 4096 rectangles. This extreme dimensionality reduction forces 16.7 million trainable parameters to plummet to approximately 65,000. Because the training setup is entirely isolated, the massive frozen base matrix can be heavily compressed. This leads to QLoRA, where 4-bit normal float quantization is applied to the frozen weights, while the tiny A and B matrices remain in high precision. During inference, these small matrices are simply multiplied together and added back into the main weights. This matrix decomposition completely isolates the model's generalized intelligence from its task-specific instructions, making local GPU training mathematically viable. The theoretical math is elegant, but we have to ask if this extreme parameter reduction damages real-world performance. Benchmark tests run on the Llama 2 model series, specifically the VIGO dataset and SQL generation, provide the baseline. This chart shows Llama 2 performance across 7, 13, and 70 billion parameter models. Notice the minimal height difference between the full parameter and LoRA bars. This success highlights a specific functional pattern. These datasets require mapping existing logic into a strict structural format like SQL. The limits of this architecture become apparent when we introduce the GSM-8K, grade school math dataset, a stress test for complex reasoning. This new chart highlights a massive performance gap. When forced to do math, the LoRA bars for the 7B and 13B models fall far short of their full parameter counterparts. The failure suggests that math requires rigorous logic and the encoding of entirely new skills. A low-rank approximation physically lacks the adaptation capacity to encode dense, complex reasoning. LoRA is flawless for teaching a model how to speak, but it lacks the capacity to teach a model how to think. This establishes a hard boundary on its utility. Beyond capability limits, the LoRA training process itself contains hidden dangers. Because LoRA operates in a severely constrained parameter space, its optimization landscape is highly volatile. The industry standard learning rate of 1e to the -4, which works reliably for standard fine-tuning, is often dangerous here. This Langgraph tracks training loss over time. Applying that aggressive 1e to the -4 rate causes the curve to explode upward into severe instability. Dropping the learning rate to 3e to the -5 forces the model into a stable convergence, flattening out at the minimum loss. Alongside lower learning rates, engineers rely on strict task description prompting. Describing the task in the prompt helps the model condition its answer on the question, reducing the optimization complexity for the LoRA layers. Maintaining LoRa's compute efficiency requires navigating a much less forgiving optimization landscape than traditional training pipelines. Deployment in production shifts the focus from the training phase to the realities of the serving environment. Attempting to host dozens of specialized, full-parameter 70 billion parameter models in a data center requires astronomical storage and VRAM costs. LoRa solves this by keeping the base model entirely static in VRAM. Incoming user requests can dynamically hot swap microscopic 50 megabyte LoRa adapters onto that single base model in milliseconds. Hosting 20 distinct full models requires terabytes of space. Hosting one base model with hundreds of adapters fits effortlessly on a single node. This approach shifts the infrastructure requirements from hosting one massive model per task to one efficient base model serving an entire organization. Before finalizing a deployment pipeline, we have to address a common architectural fallacy: attempting to use fine-tuning to teach a model new factual knowledge. When a model adjusts its weights to memorize a specific set of new facts, those updates often interfere with the mathematical representation of prior knowledge. As the new data replaces foundational patterns, the model's general intelligence degrades, a phenomenon known as catastrophic forgetting. The definitive pipeline rule is to rely strictly on Retrieval-Augmented Generation, or RAG, when an application requires dynamic facts or knowledge injection. Conversely, deploy LoRa for behavioral formatting, for structural mapping, and precise tone adaptation. By respecting the mathematical boundaries of the low-rank approximation, engineers can stop fighting the architecture and deploy pipelines that are both computationally cheap and highly specialized.